Okay, so let's get started. It's our pleasure to have Professor Enrique Mallada from Johns Hopkins giving the seminar today. Enrique was at Caltech as a postdoc, and he graduated from Cornell University with a PhD in electrical computer engineering in 2014. Enrique won many prizes, such as a few best paper prizes, and he was awarded an NSF Career Award in 2018. And Enrique is doing very interesting work in the areas of control optimization, network dynamics, with application to power systems. So Enrique, take it away.
Okay, thank you, Allison. And I would like to thank you and also Brian. I know he's a little bit disconnected right now, but I want to thank both of you for the invitation. It's a pleasure to be here and virtually. Okay, so the title of the talk is Embracing Low Inertia for Power System Frequency Control. And there's this particular method that I call a dynamic Droop approach. And what I would like to convey is in this talk is perhaps two things. So first one is there's a lot of concern on the issues of low inertia in the system. So this dynamic degradation that the system has because of integration of renewable energy and the loss of inertia associated with that. And what I would like to convey, and I hope I managed to do, is that there are some pros and cons related to low inertia. And so that's the number one. So perhaps it's good to focus also on the benefits of it. And the second one is that if you have a system that is losing inertia, perhaps the best control strategy is not to introduce synthetic inertia. So if I manage to convince you of these two particular points, then that will make my day. Okay, so to start with, then let me just acknowledge a lot of people that I have collaborated with in different parts of this area. So my student Yan Jiang, she's an awesome student, and by the way, she's graduating soon. If somebody's looking a postdoc, she's really awesome, and she's done the core of the work that I'm going to be talking today. So my other student Han Chung Min and Eliza, who is a ECE undergraduate that just graduated last year. So she's done also very interesting work with us on the storage side. And then collaborators, Peter from Skoltech, Richard Fates Loon, and Fernando Paganini from Universidad of Uruguay. And of course, I acknowledge to several grants that funded this research. So I understand that this is an audience that is not specialized in power systems. So I'd like to spend a few slides trying to motivate what is the problem. So the problem is control of the frequency. And I will argue that this is a problem that dated from the beginnings of power systems. And in fact, the whole control architecture around this frequency, it was built around synchronous generators, like this one I'm showing this picture that is quite old, the 1900s. And a key part of this control architecture is something that we call Droop control, which is in charge of many things. And essentially, it's in charge of making sure that supply and demand is balanced. It makes sure that all generators basically are synchronized with the same frequency. And also it's in charge of actually distributing changes in the demand across different generators. So that's what we call power sharing. But I would argue that this is perhaps something that is not initially invented for power systems. In fact, every engine that you can think of, even steam turbines before that, actually had a very similar mechanism of control. And the mechanism is fairly simple. So this is a rotating vase, and the volts, as you start to speed up, then they go up. So this lever basically goes down, this guy goes down, this guy goes up, and then you close the valve. So in a sense, whenever you see that your generator is starting to speed up, is because it's basically emitting more energy than the one that is demanded. Then you close the valve and then you slow down. And for the control audience, then this is nothing more than like a standard negative feedback. You have a generator, you measure the speed, and then you make changes proportional to the change of the speed. And therefore, that's why you have the negative slope, meaning like speeding up implies like reduction of power. Okay, so far so good, and it's very simple. And if you are not fully convinced about the mechanism, then I'd like to provide you with like a mechanical analog. So think of a generator as one of these tracks, and the goal is actually you're going uphill, and you have to push a certain load. There is some friction, like the one that you will see over here, some demand, some payload that you need to carry, and then you go with certain speed, and you have your mass, and you're exerting certain amount of force that push you uphill. And what happens in power systems is that really this load changes over time. So the drive changes over time. And you want to, despite all this, maintain the speed constant or closely regulated around a nominal of 60 Hertz of 50 Hertz if you are in Europe. And although this is not true for tracks, but the closely regulated is it's more critical in power system, because like if you go too far away from this, then you start to excite certain resonating modes in these machines, which is something that you don't want to do. Okay, it looks not so complicated, except that what you really have is really like a full network of a lot of these generators all interconnected between each other and dragging loads that are distributed geographically around the whole, like for instance, Eastern interconnection, so the east of the US or the West. So it looks like this. And so the way you really solve this problem of like making sure that all these tracks are running at the same speed is by a hierarchical structure. So there's a first stage that is called primary frequency control. That is sort of like I mentioned, this Droop control, that is this proportional feedback. And then you have an additional layer of more sophisticated control that ensures other things like making sure that the nominal frequency stays around 60 Hertz, and also some like tie lines of certain interconnections with other areas, the power that is going through these areas are maintained. So this is like a snapshot of what is like frequency control in power systems. And from now on, I really want to talk about the first part, this part of actually rebalancing power and resynchronizing generators, because as I mentioned before, this is a talk about like low inertia and the fact that there exists some dynamic degradation happening in the system that it's caused by the integration of, indirectly by the integration of renewable. And this is not like a hype, it really happens. If you look at the Nordic system in Europe, then you see frequency fluctuations deviating more and more from the 50 Hertz. Like Ireland has a limit of like how much renewable generation they allow to, as a fraction of the total load, they allow to contribute. It used to be 50, I believe that nowadays it's more around 75%. But the point is like after a certain threshold, there are concerns that the system might not recover from certain events. So they have to actually curtail renewable generation. And even in the US, while the problem is not so drastic today, there's already some evidences that there is some like a dynamic degradation. So frequency fluctuations are becoming larger and larger. Okay. So I mentioned that this is sort of related to inertia. And to try to drive this further, I'm gonna try to show an analogous that actually shows why this happened, why these behaviors indeed happening. And the closest that exists to like a generator, it's really like a pendulum. So think of this as like the mass of the pendulum, and this is like basically Newton's law. Very simple, the mass, this is some notion of friction. And I would argue that the only difference with one generator, one bus model of a power system is this M here. And I can talk about more about this, but that's not the point right now. But I will argue that that actually makes the power system like a system that is better to control than a pendulum in some sense. But I hope that you can actually see what happens with the inertia when you actually look at it this form. If you want to see like what is the acceleration of the phase of like a certain mass, then you can see that when you have a lot of inertia, then there are two things that happens. The first one is like the relative effect of the friction seems to be diminished. And this arguably it's a bad thing, but there's a good thing that is that the forces, external forces, are actually also diminished when you have high inertia. So in a sense, there is a trade-off between these two things that happens in low inertia systems, and one could try to take advantage of it. So let me give you an illustration of what I'm talking about. Okay, so this is like a very simple pendulum, heavy. This is a big pendulum. So for me, this is big. What I'm going to do is I'm going to kick it, and I'm going to see what is the response of this system for this particular pendulum. And I'm going to show you the angle, the velocity, and the forces, including the friction and the disturbance that I apply. So there goes the disturbance. And then you can see that you have friction going on here. So there's like an energy dissipation. And you also see these like angle fluctuations and velocity fluctuations going. And one thing that is interesting about this particular case is that even though the disturbance actually is prolonged over time, then the actual amplitude is not so critical. It's not so big. So it's a big pendulum. So when you push it, then it takes a lot of energy to actually to put it in motion beyond the steady state. So in a sense, like I would say that the fact that the oscillations are like bounded, not so large, it tells you that provides like this natural disturbance reflection when you have a high inertia pendulum. But also it's hard to regain steady state. So it takes oscillations and states longer and longer and longer. Okay, let's now try to see a low inertia pendulum. And this is how a low inertia pendulum looks like. And I'm gonna do the same force. And now like you start to see two differences. The first one is very large oscillations, like the amplitude of these oscillations are larger. So you can imagine why we're seeing larger oscillations also in the power system when you have less inertia. But there's something interesting going on. And I would argue that the interesting part about this is that like the disturbance actually settles down faster. In the previous like illustration, at this time they were still oscillating, and now when you have less inertia, then the disturbance actually gets reduced at a faster rate. So in a sense, like if when you have a low inertia system, then it's more susceptible for disturbances, but it's faster and easier to regain the steady state. And this is sort of the message that I will hope to convince you that something similar is happening in the power grid. Okay, so this is indeed a fact, this is happening. And it got to the point that actually the FERC and many regulatory institutions actually are requesting that renewables actually provide certain type of frequency response. So what are the challenges of this? So we're actually asking for devices that are not designed to, but I wouldn't say not designed, but that they do not naturally provide this type of behavior to actually implement it. Because of that, there are several challenges. There's issues of like, you need to take measurements to mimic this response. There's delays with these measurements. You're introducing like more sophisticated dynamics into the grid. So there's issues of stability, robustness. You want this to be in a sense like plug and play. So it's like you don't want to rely on a very particular configuration for this to work. That's important. And the last thing that I would say that is also very important is the lack of incentive. So like if you own like a renewable generation, then that is interfaced with an inverter, then your goal is actually to input as much energy as possible into the grid so that you get paid for that. And that depends on how much renewable energy is available and other things, but you want to put as much as possible. But now if you want to produce any type of response, any type of like fluctuations with respect to variations in the frequency, that means that you either need to have some energy reserve, some storage, or you need to basically derate like your inverter so that you're able to actually provide more energy than the nominal that you are providing. So either none of these solutions are actually acceptable. So that's it. But how are we proposing to solve this problem? Or many people are proposing to solve this problem is say, okay, from the dynamical point of view, like something that it's plug and play. One solution would be to basically make these inverters actually mimic the response of a generator. So if you want to put it in a picture, it will be something like this. So you have like a very sophisticated power electronics that are actually extremely fast, and you design a controller that actually makes it behave like one of these like all generators. And you get the argument. So it is one way to do it, but I always have like this analogy that to me this is sort of like saying, so I have your favorite like smartphone and you make it work like an old phone. It's like, sure, this probably is gonna work, but there are certain trade-offs and certain things of making this type of decision that actually might prevent you to actually do something that is much better. And this is sort of like what we trying to propose, is trying to say, okay, let's try to think of this as a control design problem and try to design controllers that actually achieve the performance metrics that we care about the power system. So, and what are our design objectives? Like basically exploit the capabilities of power electronics, improve dynamic performance, of course. I would say like this control effort, so in the sense like the amount of power that I need to deviate from my nominal production, it's important. And then of course the stability and robustness. And because like I don't have the whole day to talk about this, while we have been working in all these areas, I mainly I'm gonna talk about improving dynamic performance and this issue with the control effort that is gonna become more clear soon. So this is basically the summary or like the outline of the rest of the talk. I'm gonna first define what are the performance metrics that we're gonna design. What are the things that we think are good ways to capture the behavior of the power grid, and how this relates to the existing metrics that are being used today. Then I'm gonna show you that if you do this notion of virtual inertia, which is mimicking generation response or Droop control, there is some limits in performance that you can. And then show you that if you just design controllers that are slightly more sophisticated than just mimicking that response, then you can actually do systematically better than using these approaches. And this is basically based on 3 main works that I'm going to be talking today. So this one that mostly define this performance metrics that I mentioned. The second one that is about like the core controller that I'm going to talk about, like is like this dynamic Droop control. And then I'm going to talk also a little bit about some new results for like a new control that have certain additional advantages that we call frequency shaping control. So everything is available online if you want to get to more to the details of that. So I like to say that at any point, if there's any question, I cannot see the chat, but if there's any question, just shoot me, let me know, okay? Okay, let's talk about performance. So there's no better way to describe performance just to say it. So what I'm showing you here is like the frequency of several buses in the network, several measurements of the frequency that you see in the grid. And what I'm going to show you is like a particular event, which was like a San Diego blackout. That it's basically like a certain portion of San Diego gets disconnected from the grid. And therefore, that means that the generators start to accelerate because now there's no so much load. And you see 2 things, like this huge acceleration of the whole group of generators, but you also see those inter-area like oscillations that happen from one area to the other one. And in a sense, like when you see this response, this really depends on a lot of things. it depends on the generators, whether have inertia or not, sure. But it also depends on the network and the type of disturbance. So, this was a huge overshoot, arguably. But if you want to look at another type of disturbance, the sort of the mean frequency stays around, but then this like larger oscillations going on. This is the Eastern interconnection of the grid. So what I would like to propose is a set of metrics that actually can identify what is the source of the dynamic degradation and how this is affected by, say, the network, the generators, or even the disturbance. So the argument I want to make is like good performance metrics must be able to identify the source of degradation. Okay, so let me just provide you 2 slides of like what are the way we evaluate performance. And I'm going to give you like the power engineer version of this, and also like a subset of the power engineer version of this, and a subset of the control system theoretic version of this. Let me be more precise. So the first one is the response to a step response, right? And you can see this is fairly similar to what we saw with the San Diego blackout, except that inverted. And because it's really like the loss of a generator that could generate something like this. So we have the frequency, and there are several metrics that are important here. So you usually call like this point A, B, and there's also like an additional point C that is not shown here. Oh, sorry, it's here. Yeah. So in terms of the metrics that are critical here, it's like one is called like this rate of change on frequency, and it's basically how fast the maximum frequency, the maximum rate of change of the frequency. Then we have like the nadir, which is the point of the lowest frequency, or arguably the highest frequency that is achieved. And then we have the new steady state. So it's like the new frequency that's achieved after the disturbance. So this is like still like during like the first stage of the response, and it's before the secondary frequency control that I mentioned before actually kicks in. So a set of like complementary measures to this is usually when you look at sort of like an eigenvalue analysis around the steady state. So basically you look at the dominant eigenvalues and the damping ratio of those eigenvalues and try to see how these are changed by changing certain configurations of the grid. And I would say that this actually have several positive sides. It's like they're certainly domain specific. This is something that we care about because, as mentioned before, too much deviation of the frequency, it's an issue, and we also have like certain protections that basically disconnect loads, like under frequency load sheddings that we call it, and that will disconnect loads if the frequency goes too low. So we care about this because we don't want to disconnect loads because those are blackouts. And therefore, like, it's good to have these metrics that measure that. But sometimes it is sort of hard to associate this with the cost. It's a, if we have this particular overshoot, or if we have like an eigenvalue like that moves from here to here, so what is the source of that eigenvalue moving? So why is that we have like additional oscillations? Is it the network or a particular controller? There are methods to do this, but it's all numerically, and it's basically trial and error in some ways. On the other side, like you have like the other world, which is basically like the control community designing like system theoretic metrics for network systems. There's been a lot of recent work on this area. And the basic idea is that you introduce disturbances that can be noise or deltas, and then you look at the output, a certain output that you care about, frequency, losses, some measure of coherence. And then you basically compute some like system metrics that are derived from certain signals norms, like the L infinity norm, or like the L2 norms of some sort of like integration of like the output square when you have either deltas or, yeah, basically when you have deltas. So the nice thing about this type of metrics is that usually one gets like qualitative analysis that's very useful. So you can relate certain properties of like the performance of the system to parameters of your nodes, parameters of the network, and you can even do like very efficient computational methods to compute several of the things. But the point is like they're not very related to what power engineers look for. There's no concept of nadir introduced in something like this. There's nothing related to Rockhoff. These are not step disturbances, are just noise and this delta function, which are some abstract notion. Okay, so let me now like provide you like my proposal, or what are the type of metrics that we have been using, and hopefully you will see like they sort of meet like at the middle of the two worlds. So we have two type of metrics, one depending on the frequency, and these metrics basically are based on frequency variation. So this is like the frequency of one bus. And what I'm gonna do is I'm gonna decompose it in two parts. The first part is sort of like what we call like the center of inertia frequency, the system frequency, right? It's a weighted average of multiplied by the inertia of each one of the generators, and that's what we define as this. By the way, this is related to the center of inertia. This is something very well known. So, but we're going to use this. And then what we're going to do is we're going to subtract the system frequency from each individual frequency. This is at this like tilde like W. And when I measure this as some synchronization error, so this is like how much a particular bus deviates from the system frequency. So based on the system frequency, we can actually define everything that power engineer cares about. You can define Rockhoff, nadir, steady state. And in fact, like you can connect this to system theoretic metrics, all based on L infinity signal norms. And then with the error, basically what we can do is actually we can integrate this, the square of this error, and measure basically this like the sum over all the errors squared. So this some notion of synchronization cost. So it's like if this area is small, then like generators basically synchronize very, very quickly with respect to the network. Okay, so what about the control effort? I'm gonna basically use just the sum of the power inverters, the sum of the power that is coming out of the inverters. And I'm gonna call that X bar. And it has certain, after the disturbance, this will have certain behavior. And if this doesn't go back to zero, that means that you're actually like giving energy like all together. So we could measure the energy. You can also measure the steady state or the peak power. All these are metrics that are important. If you're gonna design a control, you wanna make sure that your inverters can provide that particular amount of peak power. We can again relate it to control theoretic metrics. If this confuses you, then don't worry. I just want to show you that there is a connection, and we use this in the theory, but nothing else. So this is the picture that I would like you to have. This is basically like all the metrics that we came up and we think are important when you're considering like using inverter-based control to actuate on frequency. And for this talk, I'm going to talk about one particular of those, the nadir, and basically the steady state and the peak power. So this is going to be the combination of the ones that I'm going to be talking about. And more precisely, as a benchmark, when we compare different controllers, what we're going to do is look at the controllability to eliminate the overshoot. That is like, if we want to eliminate the overshoot that is produced by in this nadir, then it's like, how much control do we need based on these different controllers that we are providing that we discussed? Okay. Okay, I need to go slightly faster. Okay, let me now show you, like, based on these metrics, how is that virtual inertia and this Droop control implemented by inverters perform. And to that, I need a model, and the model is actually very standard. I'm going to assume that I have step disturbances. So this is a vector of step disturbances that goes into each bus. And this is a linearized model of the power network. So each one of these blocks represent a bus like that has generators or one generator in a simplified version. And these are the frequency gets to the network. This integration tells you that actually the power fluctuations in the network depends on the phase, not on the frequency. And this Laplacian matrix is a linearization of the power flow equations on the grid. So nothing fancy here. It's a very well-known model, very well studied and used. So what about each one of these bus dynamics? So I'm gonna have like a generator here that gives you the frequency, and then I'm gonna be talking about grid following inverters, and I'm gonna give a very simple model for this inverter. But let me just first discuss the generators. I'm gonna mostly in the theory that I'm gonna be providing this, I'm using just like the swing equations, which looks very similar to the pendulum that I showed you before, it's just linearized. This is basically some measure of power imbalances. This is the output of a turbine of a generator, and this is like the turbine dynamics. And you can write the Laplace transform of this and look at this as some transfer function. And for the inverters, I'm gonna basically look at different simple versions that are maps from frequency to power. And this is basically a simplification, and this is mostly for the purpose of looking at the effect of changes in the power injection at the system level. And of course, like if somebody like Brian will be here, then we'll tell you that this is oversimplified. But this is really looking at dynamics that are on the order of like, I'll say, like hundreds of milliseconds to seconds. I would say mostly seconds. So it's like so this is a time scale for which this makes sense. So you can have like a proportional along all the temporal frequencies of the signal. And that's this standard Droop control. And when you're at derivative term, then it's sort of that's what we call virtual inertia. So you amplify like higher frequencies of this transfer function. And why it's called virtual inertia is because really when you look at the state space version of this, then it's sort of adding to this inertia parameter. But I would like to point out is like what happens when you implement this trivia controller. So again, so this is my controller, and it looks like adding some friction and adding some like mass. And if we go back to our pendulum example, where we have a low inertia pendulum, they had a lot of oscillation. Suppose that now we put like this virtual mass, so we add a controller that actually adds this virtual mass. So this is what happened. The upper part sort of behaves as before, as if this was a heavy pendulum, which is what we wanted because this is a virtual mass control. However, when you look at how much control effort is needed to implement such control, then you see like you're introducing a lot of power, a lot of forces in this case to produce this. And in fact, like at the end, it really is just these particular forces that actually are producing this dynamic behavior. So instead of actually settling down after the disturbance, then you still excite because of your controller. So surely, like it's good for disturbance rejection. So now we bounded this part here. So this looks nice, but when you look at the power that is being used, it could be very bad. So it's an excessive control error in this side. Okay, what about friction? If you were to look at friction, actually, well, it turns out that it looks much better in the sense that it just dissipates the energy that was in the system, and it settles down much faster. So it provides all the benefits. Disturbance rejection, restores a steady state, and also like a reasonable control effort. This is not so much compared with the other one. But is there any issue with this? And I would say that for the pendulum, no, but for a power system, there is. So we'll get to that, okay? So let's see how those strategies look like when we actually do it in a power system. And again, we're gonna look at this system frequency in the nadir, and also the power that's being produced by the inverters. I'm gonna try to see, can we kill the nadir? So there's a little bit of theory related to this, and for that we need an assumption on the transfer function of the generators and the controllers. Basically, what we're saying is that all these functions need to be proportional. They should be different up to a proportionality factor. They should be equal up to a proportionality factor that depends on the relative inertia of each one of them, of the buses. And I don't want to get in discussion, this is good or bad. The answer is probably this is a really bad assumption. But I'm going to show you that some of the things we're doing actually still work in the experiments, but also there's another more sophisticated theory that I cannot talk about this that allows you to generalize these ideas too. Okay, so why do I make this assumption? And let me just say this is because like after a change of variable in these transfer functions that you end up with a decoupled system, meaning that when you see a disturbance, then this is transforming after a change of variable in disturbances that sort of affects very simple systems that are all equal except for like a feedback here that depends on the eigenvalues of a weighted version of the Laplacian. And the interesting thing I will say is that you can see that synchronization error is only related to all the modules that depend on the network, and the system frequency only depends on the one that does not depend on the network properties. So in a way, this is like a metric that depends only on generators and inverters, and the effect of the network is actually seen by the synchronization error. Okay, so what can the theory tells us about the problem at hand? Well, for the sake of, let me just say a few things. The first one is that we can explicitly compute this step response for the system frequency in this particular case. And we can see that the role of inertia particularly is, except for the Rokoff, neither this, of course, the steady state that not depends on the inertia, but also the effect of the nadir, this overshoot, the effect of inertia in this overshoot is actually secondary, I will say. It's much more related to damping and other things. And this can be seen, for example, in this numerical illustration. What I'm showing you here is actually the nadir. And if you change the dampen, you can see that you can actually affect the nadir quite a lot. But if you change the inertia, orders of magnitude, which is unrealistic, then you, for the current operating points that we have today in the grid, then you will only be able to change like minimally. And notice that this is after like orders of magnitude change of inertia, which again is unrealistic. Similarly, if you look at the droop of the generator, they do have certain effects. But let me just keep you in mind this, is that inertia by itself is not sufficient to actually make industrial changes on the nadir, for example. What happens when you introduce virtual inertia to the system? The analysis looks very similar, except that now the inertia appears here in the Rokoff. So it is good, arguably. But the other things still not change. And in particular, we get to this result that essentially says that if you're using a control like this and you want to eliminate the nadir, this overshoot, then you need this condition to hold. And this sort of tells you if inertia is large, then this term could be negative. And therefore, you don't need virtual inertia to actually eliminate nadir. But if inertia is small, then actually this requires a lower bound on the amount of inertia needed to obtain that. So let me illustrate this with a simple example. This is the system frequency without control. This is how it looks when you add sufficient inertia. And this is how it looks if you add like Droop control. So you still have an overshoot, but you're able to stay the frequency larger. So you're achieving the same effect that you wanted, but by keeping the frequency at a new steady state that is larger, and with the same nadir. What about the power? Well, no control, there's no power. For virtual inertia, then we basically get to like almost a 0.7 per unit of the disturbance size. And for Droop control, we don't get so high, but then we have to provide like a lot of power in steady state to keep the frequency here. Okay, so in a sense, like when you look at only this friction control, this virtual friction control, the argument is that, well, it is good for this one, for the pendulum. There's still some issues related to the steady state that you need to maintain. So there's this amount of power that needs to still be sustained. Can we do better? Let me now show you like, okay, I'm doing fine. One way to do better. And this is what we call dynamic droop or iDroop, the first one. And the idea is very simple. Instead of actually having just this type of filter, let's have a slightly more sophisticated filter that comes from putting a pole that actually can behave as a lead or as a lag compensator. Fairly simple. Just make sure that you don't amplify too much higher frequencies. What happens when you do this? Well, this is how the actual dynamics look like to start with. So the power that is going to be generated by the inverter, it's defined by this equation. Not so complicated, but when you test it on the pendulum, then this is what happens. So you basically are able to eliminate all the additional oscillations that happens in the system. And the key idea of this is really like providing like friction only for a certain amount of time and then like relaxing it. And this is relaxation that basically reduce the amount of power that you need to give in steady state. So the argument is that if you have a low inertia pendulum, instead of adding mass, all you need to do is actually design controllers that are like good enough to actually to capture, to dissipate the energy that you have in this low inertia system. Okay, what we can say about like this nadir elimination based on this control? Well, it turns out that there's a way to tune the parameters that actually ensures that you eliminate the nadir. In a sense, if I set the parameters to these values, then I make sure that not only I kill the nadir, but also I make sure that in steady state, my inverters are not producing any power. So I only need to really like arrest the frequency to get to the steady state that is provided by the generators, and that's it. And there's like a very like simple explanation of why this controller works with these particular values of the parameters that are related to the turbine time constant and the turbine droop. And the reason is that when you look at the same analysis I was showing before, this has a first order step response. And it's even a more intuitive explanation that is that when you look at this controller under those parameter values, it sort of looks like a proportional control and something that sort of cancels the effect of the turbine. So at the end of the day, this is like a first order system with a proportional feedback, which is also a first order system. Okay, so let me just, I have like perhaps like 5 to maybe top 10 minutes left. Let me just try to provide some illustrations. I'm using the low inertia system, Icelandic power grid. It's fairly small. Maximum load is actually 1.3 gigawatts. And it's also fairly low inertia. So what I'm showing you here is that basically what I do in this system is the following. I reduce actually, I do not take away generators. What I do is like I reduce like half of the droop coming from the generators, and I introduce it with inverters. And then I compare in the real system without the assumptions that I made in my theory, what happens when you, for example, try to eliminate the nadir. That is like, I try to tune iDroop for nadir elimination. I also tune virtual inertia to make the system a critically damped first order response. And then I just put like the droop that is necessary to have the same steady state. So as you can see, like when you look at frequencies, then there's really not much more of a difference between any of these examples. Arguably, let's say maybe this one settles faster, doesn't have like this overshoot that iDroop, that droop control has a little bit. Virtual inertia, again, this looks like the pendulum that I mentioned before, these additional oscillations that are still staying longer and longer. And in fact, like when you look at the control effort of the inverters, you actually see that that's really happening. So it's like the virtual inertia is introducing all these extra oscillations. And of course, this is unrealistic. This is actually 1 order of magnitude larger. But this is really happening because my gold standard is removing nadir. And in this particular case, the only way you can do that is by setting for virtual inertia the nu to this particular value. And that makes these oscillations large. And on the other hand, iDroop, it sort of behaves similar to Droop control, but it doesn't have to produce a steady state. So once again, like it settles oscillations faster and then stays in the same value. And in a sense, like it leaves the steady state for the remaining generators in the system. So the control of the power of the generators are the ones that actually compensate for the power imbalance. The Droop controllers coming from the inverters only affects the transients. I can talk about a little bit about like parameter uncertainty, meaning that the trick that I mentioned is by tuning something very particularly. But when we test it, we see that there's actually, in fact, for this particular parameter, which is the critical one, there's a vast region of parameters as long as its delta is larger than the turbine time constant, that the same mechanism works. So the nadir actually stays bounded and actually it doesn't overshoot. So I talk about basically the benefits of using a more sophisticated control, this notion of like we can do this overshoot elimination. So my power engineers collaborators actually find this very exciting, and it's something that you can even do like at the system level, but also at an individual generator level, provided you have storage close enough to them. There's other benefits of doing something like this. You can actually tune for noise attenuation, disturbance rejection. Also, we can reduce interior oscillations if needed with this type of controller. But what's really missing is controlling the rock-off. So we cannot control the rock-off. So the control of the rock-off still, if it's a low inertia system, will depend on that. However, there's a different way, a slightly more sophisticated controller that actually manages to control the rock-off. And the idea is very similar, as I mentioned, for like eliminating the nadir for the iDroop, which, if you remember, was basically making this a first order equation for the system frequency. Except that now, like we want to match this to something that also changes the rock-off, which is basically this parameter over here. So that is like we want to find a controller that matches this, and the way to do this in general in control is model matching control. So it's like you solve this algebraic set of equations that matches this to this. And the good thing about this particular solution is that it sets the rock-off to be this parameter A or related to A, and the steady state depends on B. So if you happen to define your controller to be something of this form, where this is the turbine time constant as before, then there's like an equivalence between the parameters that allows you to make this system behave like as a first order system. And just to show you like a simple illustration, this is what we had before, the no control trajectory, the one that comes with critically damped virtual inertia, and this was iDroop. And we have this sort of like control effort coming from, say, the storage or like your inverters connected to renewable energy or whatever. If you do this new frequency shaping control, then you're able to change the nadir, change the rock-off without affecting the nadir. So, and there's this trade-off of you have to increase the amount of power, but that's logical. But on the other hand, like you're able to control the nadir. So it gives an additional flexibility in the control. Okay, so let me just say that this is a case where virtual inertia was not able to control the nadir, and yet like frequency shaping with the same Rokov achieves like a control of the nadir. So let me stop there and summarize so that we can have a little bit of time for questions if there's some. What we developed here was basically like we developed a set of dynamic performance metrics that are sort of like this midpoint between control and power engineering. It accounts for like the ability to identify like whether this depends on inertia, damping, or in the network. And in some sense, like it's sort of like a compromise between the two communities. I think I like to think it's doing. But then I show you that. Okay, I forgot about these takeaway messages. Yeah. So I think one of the takeaway messages that I want to say is that lighter systems are easier to control. Okay, if you have a system with less inertia, let's remember this and try to use this advantage to control it. There's actually less energy to dissipate in disturbances, and therefore we should take advantage of that. And actually, damping seems to be better than inertia in those particular type of cases. But if you are doing control, which is what I did today, then you can do much better than just adding trivial damping or adding inertia. And I show you that with iDroop, we can do nadir elimination. We can also do synchronization cost and also attenuate like frequency variance. I mentioned about like how we can control the Rokov and use the trade-off between Rokov and control effort with this frequency shaping control. And of course, this is like just like a narrow picture of a low inertia system and how to use how to shape the power that is injected by the inverters. And it's like not a full picture. We're missing like the fast time scales, absolutely important. There's a lot of issues related to how to tune inverters that actually do not induce instabilities with the lines, and among many other things. And of course, the other thing I did not talk about is much about like robust performance. So I talk about like how to tune these things. I show you slightly a little bit of if we tune in a particular way, we can do better, and that this seems to be robust, but there's way more things to make sure that these things are actually, the performance still is satisfied in a systematic way across many, many cases. So let me stop here and like leave it to questions.
Great, thanks, Enrique, for his talk. Any questions from the students first? Grad undergrad students, any questions for our speaker?
Yeah, I have a quick question.
Yeah.
So essentially when you're, I guess I found the analogy to this variable friction with the pendulum pretty helpful. So when you're implementing iDroop, if you're doing this virtual friction modulation type of control, do you have to calculate the time derivative of the frequency? And if so, do you run into any numerical issues with taking that derivative, like any instabilities because of that?
Yeah. So that's a really good question. The short answer is no. The reason why it's not, it's because when you look at this particular transfer function, this is a proper transfer function, and therefore that means that it could be realizable in state space without having to put additional derivatives on the input. So that means that you don't need to derive the measurements to do this. It's just like a proportional from the input to the output plus some additional like state-based dynamics. And you can do this. This is a standard. You can do this in control, provided that this is actually a proper transfer function. So the degree of the numerator is equal to the denominator. However, it is true that when I was showing you the second controller, then I did not have a proper transfer function. Again, the standard control trick to do something like this is like you add an additional filter of higher frequency than the frequencies that are relevant for your dynamics. And because of that, then you're basically, although the theory cannot tell you that your runoff is going to be controlled by this, in practice, because of the region of the dynamics, this works. So the runoff practically becomes equal to this. So the answer is like, no, there's no like a practical impact when you do that. And you can also change your parameters to mitigate like the amplification of higher frequency noise. Yeah, and we have done that. Yeah, but that's a really good point. I did not mention it in the talk. Yeah.
It sounds good. Thanks.
Okay, any other questions?
Yeah, I guess I have a question related to the controller. Yeah, so do you consider some bounds on the controller, such as the upper and lower limits?
You mean in the control saturations you're referring to, or bounds on the parameter values?
Yeah, so in my understanding, the controller the sensor control is the inverter-based resources, right? So yeah, so for the
I didn't get that. Could you tell me
variables that changes with the output of the virtual inertia is some power, right? So the source of the power, so the source of the power is some inverter-based resources or some other.
Okay. Yes. So in the analysis that we are showing here, I do not assume that there is saturation of the power. That is true. The workaround that we do that is that instead of doing that, what we aim at computing is that what is the peak power that your controller will have in per units on the particular units on the of your we do it in per unit. So, and we actually use this information to sort of like identify how much actual storage you need, or how much actual control effort is needed from the inverters. If this makes sense, let me be a little bit more precise. It's like so if like when you do this studies, you see that you're able to provide the performance that you want with a 0.6 per unit, then that means that I need to be able to provide such an amount of power coming from the inverters in per units. But we have not looked at the analysis of what happens when you saturate. But what truly will happen when you saturate is that any saturation on power here will actually be affected in terms of having an additional like overshoot that was not prevented. So I would say like as long as the steady state is actually well controlled, then this will not be a major issue for this particular problem. Yeah. I hope this answered your question. And
yes.
Okay.
Yeah, and I'm also curious, if considering the storage, then there's other limits on the storage, such as the total charging and discharging. Yeah, so if there's this kind of issues. So
yes, absolutely. Like you need like okay, so what you are seeing from these controllers is that the type of like storage that you need is a storage that it's able to produce like high power, and it doesn't need to provide it for a very long amount of time. So if you were to implement with this with storage, then I would say that you should have that storage being used for something else. And also, like whenever this actually happens, like activated to provide this support. Having storage just to do this is, well, it's gonna work. It shouldn't be just the only purpose of that. You could also try to release some of the energy. So people have done this of trying to look at whether some of the energy could come from the inertia of like the wind turbines that you have. that is also possible at a certain extent. And actually, wind turbines will be a different way to try to implement this type of control, in which you need to have like a quick release of power, but then you can settle down to zero in terms of the amount of extra power that needs to be released. I actually talked with Lucy Powell about some of the things and whether this will be useful for those type of things from Boulder. Yeah, but there is, yeah, the answer is like you have to design the storage, like the control and the amount of storage that you put in the system properly, in a proper way. And what is that proper way is that you need to have sufficient storage, for instance, if you were to do it with storage, so that you do 0.6 per unit in terms of the imbalance. So it's like, what is the disturbance that you have in the system?
Yeah, thank you very much.
Okay.
Okay, any other question from the students?
I think there's a question in the chat. It says like,
right.
In one of the examples of constant damping control, there seemed a steady state error in the step response. I may have missed a diagram, but if not, can you explain again why that will happen in this power system? Yeah, so when you have like this constant, this proportional feedback, I guess like if you look at it from the point of view of the control side, like proportional feedback is not usually sufficient to bring the error back to zero, right? Usually you do that with additional type of like integral control or other things. I'm not saying we should do that here, but primary friction control that does with proportional feedback still has a certain amount of power that in steady state needs to be provided by the inverters. Think about this way: when the frequency goes down and settles in a new value, there's a constant deviation from the nominal, and that constant deviation from the nominal implies that your proportional controller will have to give constant amount of power in steady state. Does this help, William?
Yes, that does. Thank you. I thought that the damping was more of a derivative term, so that's what I was thinking of.
Yeah, it's confusing because I put it as a derivative term, but with respect to the phase. And in power systems, like, yeah, so it's a frequency that stays constant, deviated. So that's why it stays active. Yeah, that's another way to put it. Yeah, in power system, you do have that additional part. Yeah.
Okay, so I think for the students, you're free to go. And the rest of us, we can hang out a little bit longer for more questions. So Enrique, there's a direct question. And Max asked, can iDroop be self-tuning as the system characteristics change over time? So basically, can it be self-tuned while the system changes?
So can it be self-tuned? I mean, I think it can. So there's a lot of work that have tried to look at how to basically try to determine system parameters from measurement noise or frequency of fluctuation. So people try to guess whether the turbine times constant or the aggregate, so some notion of time constant coming from the system out of like measurements that you see from PMUs or other things. You could use that to actually tune the things to actually produce a better response. Yeah, and I would say like the other advantage, which is something that I have not talked too much, is all this depends on the system frequency, and the system frequency, it's sort of like the response of an aggregate of generators, and as such, it does not depend much on the composition of the generator, but rather some aggregate measure of that. And because of that, then like it's fairly easy to get like a model that actually works sort of okay, provided that you have an idea of what are the time constants in your network. So I'm happy to give more details, but yeah.